So this is the last section of your 3.2 notes, the theory of plate tectonics. So let's actually start with the question that we ended with part 2. Where are the most active volcanoes and earthquakes located? Well, let's think about it. Where do you think you're going to find the most activity? Now we're talking about plate tectonics, so the answer is going to be at plate boundaries. So most active volcanoes and earthquakes are found at plate boundaries. So anywhere you see, like for instance, this is the North American plate, that is actually notified by all of these earthquakes and volcanoes. The volcanoes are in red, and then the earthquakes are in blue. So this one is the North American plate. Here is the Pacific plate. Notice how all of these earthquakes and volcanoes occur. Here is the South American plate, again divided by lots of earthquakes and volcanoes. All right. So let's go through the last section of your notes. Obviously, again, the biggest thing about plate tectonics is explaining how the plates actually move. Well, there's 3 proposed processes that scientists possibly explain that possibly cause how the tectonic plates move across the Earth's surface. And these are the 3. So we're going to go through each one individually. And if you're looking at your notes, this is the bottom of page 5, and we're going into the top of page 6. The first one is going to be number 1, mantle convection. Okay. So with that one being said, let me review a video clip with you guys. So let's see here. Here you've got the process of convection, okay? Notice how, again, you have 2 cells. One's going one direction and the other one's going the other direction. With that being said, as you see at the very top of the screen, notice right up here how the plates are actually pushing away from each other. Okay, here you've got all of this convection happening in the asthenosphere, and then here you've got the lithosphere being moved apart. So again, notice that kind of like these are circles and these are circling the opposite direction, pushing these 2 plates away from each other. So this is one plate and this is another plate. Okay. So with that being said, if you remember last year, for the students I had last year, this one's also another example of how you see convection, because again, think of the mantle like a putty-like material. So watching this one, okay, again with this one, convection occurs because of differences in density of these 2 liquids, okay? Warmer liquid is going to rise because it's less dense. Cooler liquid is going to sink because it is more dense. And eventually, as the cooler liquid warms up, it's going to rise. And as warmer liquid cools, it's going to down. Hence the terms heat up, cool down, all caused by the differences in temperature and densities of these waters. So the density changes because the temperature changes. Okay. Moving on. The second proposal of how the plates move is something called a ridge push. This one's a little bit more complicated to explain. Ironically, this is a newer idea, a newer piece of evidence that occurred. When I say newer, it's 1990s. It's not easy to come up with new evidence. So this is pretty recent when it comes to science proposals in terms of evidence. So the idea is that the oceanic lithosphere thickens with distance from the mid-ocean ridge, which means like it gets thicker closer to the trench and thinner at the ridge. So this causes the plate boundary between the lithosphere and the asthenosphere to become deeper, farther from the ridge. This allows rock near the crust of the mid-ocean ridge to slowly slide down the slope of a ridge, pushing the older organic slab in front of it. Okay. Along with it is something called a slab pull. Now, right now, you're probably like, oh my gosh, this is a lot of information. Well, I'm going to show you a video to help you with that. But let me show you what I mean by a slab pull. When an oceanic slab moves away from the mid-ocean ridge, the slab becomes increasingly colder and dense. Well, what do we know about colder and density? Well, that means that the slab is going to subduct, which means sink. The colder, denser oceanic lithosphere sinks into the hotter, less dense mantle and pulls the rest of the slab downward with it. This process is known as a slab pull. So literally it's going to pull this part of the rock down because it's cooler and more dense. So it's just going to pull it down. So that's a slab pull. And then a ridge push is literally like the thinner crust is going to push the older crust away, not just by convection, but literally the ridge is pushing the older crust away. So that's what a ridge push and a slab pull are. Okay, so there's a video clip that actually might explain this a little bit better. So we're going to go ahead and pause and then watch the next section of this video. And the person does talk a little quickly. So later on, if you find that after watching it as a class once, you need to watch it again, you can always go back and replay it. All right, so watch the next video.
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
So the last part of these notes, I actually just want to see if we can I can quiz you guys mentally, not a real quiz, but mentally, to see if you remember some of the topics that we've talked about in this set of notes. For instance, here's first question. Do you remember what the 3 pieces of evidence that supports the theory of continental drift? In your head, I want you to think if you can remember that. If you can, then you should have remembered that they are fossils, climate, and land features. Okay, fossils being fossils found in 2 different areas of the world that are now currently separated by large bodies of water. So that must support the idea that those continents must have been together at one point in time. Land features would be like how Africa fits right up against Europe and North America as well. I'm sorry, South America butts up right against Africa and North America against Eurasia or Europe. And then obviously climate, how we found coal beds in Antarctica that currently is in a very cold climate, and coal beds can only be formed if it was found if Antarctica was actually closer to the equator, because coal is actually the creation formed by animals and plants decomposing. Okay, so what pieces of evidence support the theory of plate tectonics? This one's a little different. So if you remember, the first piece of evidence is seafloor spreading, the idea that the plates separate from each other caused by the process underneath the Earth's crust. And then the second piece of evidence is earthquakes and volcanoes and where they're located. So that shows evidence that the Earth's crust is made of plates. Okay, true or false, according to seafloor spreading, this should say older dated rock can be found closer to the mid-ocean ridge. The answer is false, because older dated rock is actually found closer to the trench where you have subduction. Next question. The three processes that cause tectonic plates to move are convection currents, ridge push, and slab pull. The answer is true. These are the three processes that we just went over to explain how the plates actually move. Okay, in convection, any movement of matter that results from differences in what? So the answer to this question is differences in density. So again, how warmer water, warmer mantle rock, we call magma, rises because it's less dense, and cooler magma sinks because it's more dense. So the answer to this question is density. The main source of heat for convection currents is the what? Well, the main source of heat actually comes from the core. Convection currents are found in the mantle, so its main source of heat is actually the core. And what is that force that causes convection cells to turn down? Well, there's only one force we talk about when it comes to the Earth, and that force is gravity. It's what pulls everything down to the center. Okay, and last but not least, let's see if you really get challenged. Convection currents occur in the mantle and in our atmosphere. The answer is true. This is actually convection currents as long as there's changes in differences in temperature and density and occurs in a liquid, then the answer is going to be true. You can have it in the mantle and in the atmosphere. Okay, so there is a checkpoint that you have that you need to complete in Schoology. So make sure you complete that. And yes, you are allowed to use your notes for this checkpoint. It's just to make sure you stay on top of your understanding. All right, good luck, guys.